Welcome back. Today we're exploring domain adaptation, how to take a general purpose language model and specialize it for specific domains.
Domain adaptation is crucial because general models, while capable, often underperform compared to domain specialized models in fields like medicine, law, or science.
Let's start with the fundamental question, what makes a domain different?
Domains differ in vocabulary, writing style, reasoning patterns, and background knowledge.
Medical text uses specialized terminology, follows specific documentation formats, and requires domain expertise to interpret correctly.
Legal text has its own jargon, formal structure, and requires understanding of precedent and statutory interpretation.
Scientific domains have specialized notation, methodological conventions, and domain specific reasoning.
Even within broader domains, there are subdomains. Medical imaging reports are different from clinical notes, which differ from research papers.
So, how do we adapt a general model to these specialized domains?
The typical approach has two stages: domain adaptive pre training, followed by task specific fine tuning.
Domain adaptive pre training means continuing the pre training process on domain specific text.
You take your foundation model and train it further on medical literature, legal documents, scientific papers, or whatever your target domain is.
The objective is still next token prediction or masked language modeling, the same as pre training, but on domain data.
This helps the model learn domain vocabulary, common phrasings, and implicit knowledge without forgetting its general capability.
The key is using a much lower learning rate than initial pre training and not training for too many epochs.
If you train too aggressively, you risk catastrophic forgetting, losing the general language understanding that makes the model useful.
After domain adaptive pre training, you typically do task specific fine tuning on your actual downstream task.
For example, after pre training on medical text, you might fine tune on medical question answering or diagnosis suggestion.
Let's talk about data for domain adaptation. What kind of data do you need?
You need large amounts of domain text. For medical adaptation, this might include PubMed articles, medical textbooks, clinical notes if available, and health web content.
For legal domains, case law, statutes, legal briefs, and contracts.
For scientific domains, research papers from ArcSafe, specific journals, or domain specific repositories.
The data should be cleaned and potentially deduplicated, just like general pre training data.
But domain data often has special challenges. Medical notes might contain PHI, protected health information, that must be removed.
Legal documents might have confidentiality concerns.
Scientific text might include equations, figures, and tables that require special handling.
Tokenization can also be a challenge for domain adaptation.
General purpose tokenizers might split domain specific terms inefficiently.
The term acetyl salicylic might get split into many pieces, making the model less efficient at processing medical text.
Some approaches retrain the tokenizer on domain text before adaptation.
Others use domain specific tokenizers or extend the vocabulary with domain terms.
But changing the tokenizer means you need to reinitialize the embedding layer, which can hurt transfer learning.
There's a trade off between tokenization efficiency and leveraging pre trained weights.
Let's discuss mixing ratios for domain adaptation.
Do you train purely on domain data or mix in general data?
Pure domain data risks forgetting general capabilities. The model might improve on domain tasks but degrade on general language understanding.
Mixing in some general data during adaptation helps maintain broad capabilities.
Typical mixing ratios might be 80-90% domain data, 10 to 20% general data, but this varies by application.
Another approach is curriculum learning. Start with more general data and gradually shift to domain specific data.
This can help the model smoothly transition from general to specialized knowledge.
Let's talk about evaluating domain adaptation.
You want to measure both domain task performance and retention of general capabilities.
Domain benchmarks might include domain specific QA, classification tasks, or information extraction.
For medicine, there are benchmarks like MedQA, PubMed QA, or clinical note understanding tasks.
For law, there are legal judgment prediction, case outcome prediction, or contract analysis tasks.
You should also evaluate on general benchmarks to ensure you haven't degraded broad capabilities.
Now, let's discuss parameter efficient domain adaptation.
Instead of adapting all parameters, you can use peeved methods like LoRa or adapters.
Train domain specific adapter modules while keeping the base model frozen.
This is memory efficient and allows you to maintain one base model with multiple domain adapters.
You can swap adapters for different domains or even combine multiple adapters for cross domain tasks.
Another technique is domain specific prompting.
You can prepare domain context to inputs like you are a medical expert assistant to shift behavior.
Soft prompt tuning learns continuous prompts that specialize the model for the domain.
These prompt based methods are extremely lightweight but might not achieve the same performance as full adaptation.
Let's discuss multi domain adaptation.
What if you need to adapt to multiple domains simultaneously?
One approach is multitask learning on domain specific tasks from different domains.
The model learns shared representations that benefit all domains plus domain specific parameters for each.
Another approach is modular adaptation, separate adapters or experts for each domain.
A gating mechanism or explicit selection determines which domain module to use for each input.
This allows specialization without forcing the model to compromise across conflicting domain requirements.
Let's talk about cross lingual domain adaptation.
What if your domain data is primarily in one language, but you need to support multiple languages?
Start with a multilingual foundation model, then do domain adaptation on available domain data across languages.
The model can transfer domain knowledge across languages through the shared multilingual representations.
If you have more domain data in one language, the model will learn domain concepts there and transfer them to other languages.
This is particularly valuable for low resource languages where domain specific data is scarce.
Another consideration is temporal domain shift.
Domains evolve over time, medical knowledge advances, laws change, scientific fields progress.
Models trained on older domain data might become outdated.
Continual domain adaptation involves periodically updating the model on recent domain data.
This requires balancing new knowledge acquisition with retention of established knowledge.
Let's discuss knowledge injection for domain adaptation.
Sometimes you want to inject specific structured knowledge, ontologies, knowledge graphs, or domain specific rules.
One approach is to augment training data with knowledge grounded examples.
Another is to use retrieval augmented generation, where the model can query domain knowledge bases at inference time.
This allows the model to access up to date domain knowledge without retraining.
Some approaches use hybrid systems, neural models combined with symbolic reasoning or rule based components.
These can enforce domain constraints or ensure outputs conform to domain requirements.
Finally, let's touch on evaluation beyond accuracy.
In sensitive domains like medicine or law, you care about more than just task performance.
You need to evaluate safety. Does the model avoid harmful recommendations?
Calibration is the model appropriately confident or uncertain.
Faithfulness. Does it ground responses in domain knowledge rather than hallucinating?
And explainability, can domain experts understand and trust the model's reasoning?
So, to recap, domain adaptation involves continued pre training on domain text, followed by task fine tuning. It requires careful data curation and mixing ratios. Parameter efficient methods enable maintaining multiple domain adapters. Multi domain and cross lingual adaptation extend to multiple specializations, and evaluation should cover both performance and domain specific concerns like safety and faithfulness.
Next episode, we're diving into parameter efficient fine tuning methods like LoRa, adapters, and prompt tuning in detail.
Thanks for listening. Until next time, keep learning and stay curious about AI.